Uh, can you see my screen? Is it shared? Okay, fine. So you can see the title now. That's great. So so okay.
Good afternoon, everybody. So I am very happy to introduce Professor Mujahid Abbas, Professor of Applied Mathematics, University of Pretoria, South Africa. He has completed two PhD. One is the Applied Mathematics in National College of Business Administration and Economics, Pakistan, and another one is PhD in Mathematics, University of Politecnica de Valencia, Spain. He has produced 9 PhD in the field of fixed point theory and its applications and fuzzy logics. So also he has published more than 367 papers in reputed journals with high impact factors. So he has completed 5 major research projects for various government funding agencies, and he has organized 5 workshops and 3 international conference and 1 is symposium. So he has selected and availed the postdoctoral fellow and visiting professor scheme in various countries like UK, USA, Spain, South Africa, Vietnam, Romania, and Turkey, etc. So now I request the Professor Abbas to deliver the lectures. Thank you.
Thank you.
Thank you.
Thank you, Professor Prakash, for your introduction. And then I really feel thankful to the organizers of this conference. They organized the conference in a very nice and very well organized manner. I really appreciate the work carried out by these 3 very dynamic, figures behind the organization of this conference. Principal Mutumani, and then convener Ratina Kumar, and then Hare Krishna, co-convener of this conference. I really appreciate it. Is not an easy task to organize a conference, especially these challenging days we are passing through. I wish you all to remain safe and protected during this very difficult time. And then if Professor Banerjee is around, and even if he's not around, please convey my message of condolence to Professor Banerjee for the demise of his mother. It is really very unfortunate, and it is really very saddening for all of us that our colleague has lost her mother. If you look at the title of my talk, it was all about the equilibrium point problems and its equivalent form. The theme of this talk will be basically how unified this equilibrium point theory is. This is really very important to learn that this equilibrium point problem unifies a lot of research areas some of which I will discuss over here. So first of all, I will be talking about the equilibrium point problem. Then we will talk about the convex optimization problem. Fixed point problem. Yesterday, Professor Rosanna had been talking about this fixed point problem as well. Then saddle point problem. And finally, we shall talk about the Nash equilibrium problem. And then you will see how one theory unifies several other theories in a one go. So let's start with this definition. Very simple definition, which will cover a lot of mathematics. How? Let's see. We have two host of topological vector spaces. When I say that we have the host of topological vector spaces, simply mean these are the spaces where the points of the spaces can be separated with the help of some open neighborhoods which are disjoint. Simple. And then when we talk about the topological vector spaces, it simply means we have a vector space, but there are two operations called addition and scalar multiplication. These two operations are continuous with respect to the topology given on these spaces X and Y. Now, what is the second ingredient? Second ingredient is K is any non-empty compact and convex subset of X. So what do you mean by convex subset? Is a very simple set having a very simple geometric structure. It simply says whenever you take 2 points on a set and you join them with the help of a straight line, that straight line will entirely be sitting inside this set K. And when you talk about the compactness is simply a, what should I say, the analog of a finite set when you talk about, when you go to the infinite dimensional spaces or some finite dimensional spaces. So sort of analog of finiteness is there. Not exactly, but this is just to give a motivation of this set, which is a compact set. Then we have a proper closed and convex cone of Y, whose interior is not empty. Let me talk a bit about this. When you say this is a convex cone, or when we say this is a cone, this simply means you take any vector in this set, take its scalar multiple of the vector, where scalar is some positive number. That scalar multiple of the vector must also be the part of that set. So this is simply the concept of a cone. So whenever you take any vector in a set, take some positive scalar, multiply that positive scalar with the vector, the resultant vector must be an element of this set. So this is simply a cone. And when you say the convex cone, it simply means whenever you take two vectors in a cone, their sum must be in this set. So this is a convex of, this is the concept of the convex cone. Closed, you know, it's very simple. This is the proper closed and convex cone whose interior is not empty. Then, with the help of this cone, we define the order. So this is something which is really very important if you are given some topological vector space, you are given some Hausdorff topological vector space, or you are given some Banach space, you are given some Hilbert spaces, and you want to define the order on that space. So the order is defined with the help of the cone. How? You say the two vectors x and y, x is less than or equal to y if and only if y minus x belongs to the cone. So very simple. If you take the difference of two vectors in a way that y comes first and x comes later, this difference must be an element of this cone. So this is how we define the order. One very simple example. Suppose you take the collection of all square matrices, fine, and then the collection of all positive definite matrices. This is an example of a cone. So this is a proper closed and convex cone. Then if you want to define the order, you say one matrix is less than or equal to another matrix if and only if the difference of these two matrices is positive definite. So this is how you can decide one matrix is less than the other matrix. In a similar way, you can define one sequence is less than or equal to another sequence. In a similar way, you can define one function is less than or equal to another function. So this tool or this mechanism will help you in deciding which element is greater than the other element. So you define the order like this. So this is a binary relation and this is a partial ordering. So this relation defined with the help of this proper closed and convex cone is a partial ordering. Then this partial ordering will be anti-symmetric if P is a pointed cone. What do you mean that P is a pointed cone? P is a pointed cone mean if you take P intersection minus P, that intersection contains only the origin. That contains only the zero vector. So if you take P intersection minus P, that intersection is the zero vector. Fine. So if this happens, then that cone is said to be a pointed cone. I give you a very simple example if there are some undergrad and graduate students around. Very simple example is your positive x-axis, if you take xy plane, then your positive x-axis is an example of a cone, your positive x-axis. And if you take the intersection of positive x-axis and negative x-axis, the intersection of positive x-axis and negative x-axis is the origin. So your positive x-axis is an example of a pointed cone. So if your cone is a pointed, then this partial ordering will be anti-symmetric. Fine. One another example of a cone. If you go in a xy plane, the first quadrant where x is positive, where y is positive, so your first quadrant is an example of a cone. Okay, so having said this, so this binary relation defined above is a partial ordering. Moreover, it is anti-symmetric if P is a pointed cone. Then you have some more ingredients to this definition. So look, what we have done so far, we have two Hausdorff topological vector spaces. We have a proper closed and convex cone. With the help of a proper closed and convex cone, we have defined the order. And now we have three more ingredients. Look at these ingredients. First ingredient is the mapping phi, which is from k cross k to y. I mean, phi will be acting on an ordered pair and will be giving you the vector in y. Then there is another mapping psi, which is from K to Y. Then this is some strange guy, which is a mapping T. T is a mapping from K to LXF. LXF means this is the collection of all linear functions from X to F. F is the field on which your vector space X is defined. You can make the things more difficult. You can take LXY as well, being the collection of all linear mappings from X to Y. You can take the collection of all bounded linear functionals from X to Y. So it is up to you, but I have taken a bit simplest case. So please remember, so far we have two host topological vector spaces, we have the order, and we have three mappings, phi, psi, and t. What is generalized mixed vector equilibrium problem? Here is the definition. So please remember this definition. My coming slides will be based on this definition. What I'm saying, we are interested in finding a point in K. We are interested in finding a point in K, a vector in K, which satisfies this condition. What is this condition? When phi will be acting at X star Y, you add it plus psi of Y minus psi of X star plus E, the duality pair of Tx star and Y minus X star. You add all these four elements, the answer is in the cone for all Y belongs to K. What is E? E is coming from the interior of the cone P. So if you can find such a point, then you have solved generalized mixed vector equilibrium problem. So this is your generalized mixed vector equilibrium problem. So it simply says, go and find a point in K having this condition. What is that condition? Condition is phi acting at X star Y plus psi acting at Y minus psi acting at X star plus E. And then this is the duality pairing Tx star Y minus X star. If you add all this stuff, the answer is in P for all Y in K. If this happens, then you have solved a generalized mixed vector equilibrium problem. I hope this is clear, because my whole lecture is based on this slide. So I quickly refresh the things. We have two host topological vector spaces, we have order, then we have three mappings, and then we are looking some point in a K satisfying this property. And if this property is satisfied, then we say we have solved the generalized mixed vector equilibrium problem. And we shall denote this generalized mixed vector equilibrium problem by G stands for generalized, M for mixed, V for vector, E, P for equilibrium point problem. And then you can find there are three ingredients written inside phi, psi, and T. These are three mappings which are involved in this definition. Why this generalized mixed vector equilibrium problem? This unified model of several problems, such as generalized mixed equilibrium problem. I will explain this. Vector optimization problem, fixed point problem, vector variational and complementarity problem, saddle point problem, John-Nash equilibrium problem. So you will find that this, my first slide, will give you a lot of research areas such as generalized mixed equilibrium problem, vector optimization problem. Then you will find complementarity problem, so on and so forth. Now, very special case. Special case is, in my previous slide, you can take X to be a real Hilbert space. Please recall that I have taken X to be host of topological vector space. You can take X to be real Hilbert space. Fine. You can take X, Y, and H same. These all are the real Hilbert spaces. Then you can take mapping T from K to H. You can take mapping T from K to H. In this case, the duality pairing mapping will become the inner product. So, and K is same as, so if you please allow me quickly, this set can be replaced with the Hilbert space H. Fine. So T will become mapping from K to this Hilbert space. Fine. And then this case will be very simple. This duality pairing will become inner product. So now please read this problem again. What does this say? It says phi acting at x star y plus psi of y minus psi of x star plus E, inner product of these two vectors, and this answer goes in the cone when E is coming from the interior of the cone. So look, the problem has become a simple when you take X to be a Hilbert space, Y to be a Hilbert space, and both Hilbert spaces are same. The only difference which it will make is the following. Instead of taking the duality pairing, you will be talking about the inner product. So this is not that old story. Sean and Hong studied an iterator method for approximating the solution of generalized mixed vector equilibrium problem, fixed point problem of non-expansor mapping, and variational inequality problem of alpha inverse strongly monotone operator. So recently, an iterator method was developed which approximate the solution of generalized mixed vector equilibrium problem, fixed point problem of a non-expansor mapping, and variational inequality problem of alpha inverse strongly monotone operators. Look at another very simple case now. More simple case. Replace your Y. Y was your host of topological vector space. Take Y equal to set of four real number. Fine. Take your cone to be R plus, say, a positive x-axis. Fine. An element E in the interior of the cone K, in the interior of the cone P has been taken equal to 1. Then your generalized mixed vector equilibrium problem will take the following shape. I think now it is very easy to understand what is generalized mixed equilibrium problem. What does it say? Phi acting at this ordered pair, psi acting at y, minus psi acting at x star. Then you take the product of these two, tx star and y minus x star. This answer must be greater than or equal to 0. This sum must be greater than or equal to 0 for all y in K. So in this case, this is called generalized mixed equilibrium problem. So you would have observed that this problem, which was presented in 2008, is the special case of the problem which I have presented earlier on the first slide. This problem is called the generalized mixed equilibrium problem. and we denote it by GMEP, phi, psi, and t remain as it is. Now, make the things more simple. Look at this problem now. If you take your psi of x equal to 0 for all x in K, fine. Your mapping T is identically equal to 0, mean T of x equal to 0 for all x in K. Then what will happen? Your generalized mixed vector equilibrium problem, depending on 3 elements phi, psi, and tau, reduces to the following problem. Very simple problem. So you are interested in finding a point x star in K such that phi of x star y, this belongs to P for all y in K. Mean you apply your function phi on the ordered pair x star y, the answer must be in the cone for every y in K. If it happens, then you say that your vector equilibrium problem is solved. The above problem basically is called the strong vector equilibrium problem, and you denote it by VEP phi. So you can see now there is only one ingredient left, phi, because you already have said that your psi of x is equal to 0. You have said your T of x equal to 0. So these mappings are identically equal to 0. You are left only with one mapping phi. And phi acting at x star y, if this goes in a cone, for all y in K, this means you have solved your strong vector equilibrium problem. So this is a vector equilibrium problem. Now I come towards a very well-known equilibrium problem which was introduced in 1994. What does this say? It simply say, take y equal to r. Take your cone equal to r plus. In your previous slide, please, if you go to the previous slide, I have taken this cone P. I have taken this cone P. But in my next slide, I'm replacing this cone P with r plus. If I replace my cone P with r plus, what do I get? I get this problem. So that's all. This is the equilibrium problem. So what does it say? It say take y equal to r, take p equal to r plus, take your mapping phi from K cross K to R, then your vector equilibrium problem will take the following shape. So please remember this line now. It says you are interested in finding some point in K. How? Such that phi acting at x star y must be greater than or equal to 0 for all y in K. So this is very simple problem. Very simple problem, but now I will show you how significant this simple problem is. How significant this simple problem is. This is what you will see right now. So this above problem will be named as a scalar equilibrium problem, given the fact that previously we had said the vector equilibrium problem, the only difference between the scalar equilibrium problem and vector equilibrium problem is that we have replaced our cone with r plus. So if you replace your cone with r plus, then this will become a scalar equilibrium problem. You can define this equilibrium problem in this fashion as well. This is another way of defining the equilibrium problem. At the start of my lecture, I have taken K to be a subset of X. You can replace this K by two different sets. I mean, you can take A, you can take B. So you can take a mapping phi not from K cross K to R. You can take mapping phi from A cross B to R as well, where A and B are non-empty set. Then you will be interested in finding some X star in A such that phi of X star Y belongs to B, because you are now fixing the first component and then you are varying the second component. So this problem is also named as the equilibrium problem. So there are one way or other. This is a special case. This is the special case of this problem, because here I have taken A and B equal to K, but you can take A and B to be two different sets as well. So this is your equilibrium problem. Now, using this equilibrium problem, let me talk something about the existence of the solution of this problem. When you say that you can find the solution of this problem, I mean, is it always possible to find some point X star in K or X star in A such that phi of X star Y is greater than or equal to 0? This is one thing. The answer is based on two techniques. There are two ways, please remember this fact. There are two ways we can prove the existence result. One is using fixed point results. So if I go towards using fixed point results, so first result which you will notice is given by Keyfan in 1972. In 1972, this set K was taken to be non-empty compact and convex set in X. And if I go towards the mapping, if you allow me to look at this mapping, please look at this mapping. Phi is a mapping from K cross K to R. And I take this K to be non-empty compact and convex set. And this mapping phi satisfies three properties. I have not mentioned three properties over here, but let me briefly explain you what are those three properties. One property is, in first argument, this mapping is upper semi-continuous. Please, if you can recall the previous day section, when Rosanna was delivering her talk, she mentioned a fuzzy number, and fuzzy number, one of the property of the fuzzy number, she was taking that this is a upper semi-continuous function. So this is a upper semi-continuous function in first argument. And in second argument, this is quasi-convex function. When I say this is quasi-convex function simply mean that whenever you take the level sets of a function, mean you take the collection of all vectors for which f of x is less than or equal to some real number a, and this level sets are convex for every real number a, then such a function is said to be quasi-convex function. So in second argument, you have a quasi-convex function. In first argument, you have a upper semi-continuous functions. And when your function phi is acting on the diagonal elements, when I say the function phi is acting on the diagonal element, it simply means it is acting at AA. It is acting at, say, 1, 1. It is acting at 2, 2. So it is acting at the diagonal element. So whenever it is acting at the diagonal element, the answer is greater than or equal to 0. Then Keyfan proved that if it happens, using fixed point theorem, he proved then equilibrium problem has a solution. So this is the one technique. If you survey the literature, you will find that Keyfan in 1972 proved this result using basically the Brouwer fixed point theorem. And you all know that what the Brouwer fixed point theorem is. Brouwer fixed point theorem simply says if you have some continuous mapping and you have some compact and convex set in Rn, or closed bounded and convex set in Rn, and your function is continuous, then it has a fixed point. So using the Brouwer fixed point theorem in 1972, it was proved that the equilibrium problem has a solution. The other technique is the separation tools. When I talk about the separations tool, one of the very basic results you will find in the literature is by Casse and Colombon in 1996. So they used the separations tool and they proved the existence of the solution of the equilibrium point problem. What did they take? They said if you take A to be a non-empty compact and convex set, and B simply a non-empty convex set. So this is the basic structure. So A is your non-empty compact and convex, and your B is simply non-empty convex. If you take this, and your mapping phi satisfy again the three properties. What are those three properties? Those three properties is your function is upper semi-continuous and concave in its first variable. Your function is convex in a second variable, and the supremum of f of a b over a for each b coming from b is greater than or equal to 0. Then your equilibrium point problem has a solution. So if you just forget this statement, remember two things. Classically, existence results can be proved using two techniques. One is the fixed point results and other is the separation tools. One was used in 1972, another was used in 1996 using the separations tool. You all are aware with the Hahn-Banach theorem, and then this Hahn-Banach theorem basically will play a very vital role in proving the existence of this equilibrium problem. Fine. So having said this, so these separation methods, as I mentioned, are based on the Hahn-Banach theorem, which simply, if I explain it in a way that it simply says that two convex and disjoint set under various assumptions can be separated from each other. So this is basically the separation axioms. I repeat it. Under certain assumptions, just forget those assumptions, there is a possibility that you can separate two convex disjoint sets. You can always, separate two convex and disjoint sets. So this is basically the separation results. And in 1996, it was used to prove the existence of the equilibrium point problem. So now I move towards the convex optimization problem. The convex optimization convex optimization problem is a special case of the equilibrium point problem. What is convex optimization problem? Look at this. Very simple. F is a mapping from K to R, including, infinity. Map can take value plus infinity. This mapping is a convex, lower semi-continuous, and proper function. When I say this is a proper function, it simply means there are some point x in the domain for which f of x, is less than infinity. The domain of f is like this set, and domain of f is, say, not empty. Okay. Lower semi-continuous function. Lower semi-continuous function, you can see is very, very, very simple. lower semi-continuous function. But just for sake of the motivations, I can simply tell you, if you draw the graph of a function, then you will find no problem at the lower side. This is what I can simply explain. Mean, if your function, if your function is not continuous, then it can have some hole, it can have some break. But when you talk about the lower semi-continuous function, it simply means when you draw the graph of the function, the hole, if there is a hole, it will be above that point at which you are talking about the lower semi-continuity, and there will be no problem at the lower side. That is why you call it a lower semi-continuous function. So you have a convex optimization problem. What is convex optimization problem? Convex optimization problem is f of x star is less than or equal to f of x for all x in k. You can find a point x star in k such that the value of the function at x star is less than or equal to f of x. Now, how this problem is linked with equilibrium point problem? Define this mapping, please. Look at this mapping. Phi is a mapping from k cross k to r, defined like this. Phi of xy is equal to f of y minus f of x for all xy belongs to k. Then look at the simple thing. This x star in k will be the solution of this equilibrium problem if and only if x star is the solution of this following problem. You can easily check, very simple exercise. If x star is the solution of equilibrium point problem, then x star is a solution of the following optimization problem. And if x star is the solution of this optimization problem, then x star is the solution of equilibrium point problem. So this is the first link which I have established with the equilibrium point problem. So if you solve your equilibrium point problem, so one way or other you are solving your convex optimization problem. And if you want to solve your convex optimization problem, then one way or other you are solving some equilibrium point problem. Now I come towards my second problem that is named as the fixed point problem. Fixed point problem simply says you take a non-empty set in H, and K is a mapping, T is a mapping from K to H. Fixed point problem simply mean find a point x star in K such that T of x star is equal to x star. I mean, you can find a point in K which remains invariant under the action of the mapping T. So you are interested in finding all those points which remains invariant under the action of the mapping T. So if you please look at your identity mapping from R to R. Your identity mapping from R to R has infinitely many fixed points. Then if you look your mapping F from, say, R to R defined by f of x equal to x squared, then you can find only two fixed points, say 0 and 1. And if you take a translation mapping, like T is a mapping from R to R defined by T of x equal to x plus 1, then it has no fixed point. In a similar way, if you take a rotation mapping, which rotate every vector on a unit circle through an angle of 45 degrees, then it has only one fixed point, which is the origin of the ball. So there are certain situations where this equation has a fixed point and this equation has infinitely many fixed points, and sometimes this equation does not have any fixed point. So there are certain situations this set can be empty, finite set, infinite set, and sometimes it can even be an uncountable set. So this is a fixed point problem. Then this is a mapping. If you take a mapping T from K to 2 top K mean collection of non-empty subsets of K. So if you take a point set mapping mean T is a mapping which is acting at a point and the answer is a set. Fine. In this case, an element x star in K is called the fixed point of this point set mapping if this is satisfied. If this is satisfied. What does this mean? It means x star is coming from T of x star. So x star belongs to T of x star. So this is called the fixed point problem for a point set mapping. Here x star is not equal to T of x star, but x star belongs to T of x star because this T of x star will be some subset of K. Fine. Look at this mapping now. I have defined this mapping in this way that phi of xy is, say, maximum of this product x minus u, y minus x, when u is coming from Tx for all xy belonging to K. So you have defined this, this mapping. Mean you are taking the product, you are taking the inner product of x minus u, y minus x, x and y are coming from K, where u is a vector which is coming from Tx, and you know that this T of x is a set. For each x in K, T of x will become a set. So u is coming from Tx. Now, this is what I really want to show you, that this x star is the solution of equilibrium point problem if and only if x star is the solution of this fixed point problem for this mapping T. So what does this mean? This simply means that if you solve an equilibrium point problem, then you can solve a fixed point problem for a multi-valued mapping. And finding a fixed point of a multi-valued mapping has its own significance and it has its own importance. If someone can recall, again, I will refer to the lecture of Rosanna. Yesterday, she was talking about a fuzzy number, which are basically the sets. And then she defined the distance between two sets. And then those fixed points over there can really give you a lot of applications in solving certain differential equations and partial differential equations, minimax problems, and other very important problems in applied mathematics. So, but what I really want to show is, I don't want to go into the discussions regarding the application of this fixed point problem. I simply want to show you that if x star is the solution of equilibrium point problem, then x star is the solution of this fixed point problem for the mapping T. Now we come towards a third problem that is named as the complementarity problem. Let me first explain you what is the complementarity problem. Complementarity problem is you take the collection of all elements in, say, H, satisfying this conditions that this duality pairing is greater than or equal to 0 for all y belongs to P, or you can take just the inner product of G and Y is greater than or equal to 0 for all y belongs to P. So this is called the dual cone of a P. So what does this simply mean? Geometrically, it simply means that you pick an element from a cone, then you find all those vectors from H. Whenever you take its inner product with those vectors, the answer is greater than or equal to 0. The answer is greater than or equal to 0 simply mean when you take the product of two vectors, you know, it simply says the cosine of angle theta is greater than or equal to 0, and cosine of angle theta is greater than or equal to 0 in a first quadrant and in the fourth quadrant. So your angle is between, say, pi over 2 to minus pi over 2. So always you find all those vectors whenever you take the product of this vector, all those vectors which when you combine with this, the angle, you know, always is between pi over 2 to minus pi over 2. So this is the dual cone of the kid. And then you have this operator T from K to H. What is complementarity problem? Complementarity problem is you find some X star in K such that when you apply T at X star, the answer must go in the dual cone of P. And when you take the product of Tx star and X star, here you have Tx star and here you have X star. X star is coming from K and Tx star is coming from the dual cone of P. Their product must be equal to 0. Fine. So these two vectors must be orthogonal to each other. So if it happens, this means you have solved a complementarity problem. So this is your complementarity problem. How it is linked with your equilibrium point problem? Here is the answer. Define a mapping phi from K cross K to R like this. Phi of X, T of X, Y minus X product. Define this. Please, this is the typo. Just ignore this greater than or equal to 0. Define phi of xy like this. Then it is a very simple exercise to show that if X star is the solution of equilibrium point problem, what does this mean? If X star is the solution of equilibrium point problem, this means phi of X star Y is greater than or equal to 0. And if this is greater than or equal to 0, consider this one, Tx star Y minus X star. Tx star Y minus X star greater than or equal to 0 for all Y belongs to K. This is the definition of phi. If you please go back to the previous slide, look at this. Your phi of xy is given by this. Your phi of xy is given by this. So if your phi of x star y is greater than or equal to 0, this means Tx star Y minus X star product is greater than or equal to 0 for all Y in K. This means Tx star Y minus Tx star X star is greater than or equal to 0, and this happens. And if this is true for all Y in K, and this is true for all Y in K, you take Y is equal to 0, you get T of X star is, say, less than or equal to 0. And if you take your Y is equal to 2X star, then you get your Tx star, X star is greater than or equal to 0. So what happens? You have shown that your Tx star, X star is equal to 0. So you have solved your complementarity problem. So what is the lesson? Lesson is, if X star is the solution of equilibrium point problem, then this is the solution of complementarity point problem. And similarly, you can go back if X star is the solution of this particular complementarity problem, then you can show that this is the solution of equilibrium point problem for this mapping phi. So far, we have proved 3 things. First, the link of your equilibrium point problem with your optimization point problem. Then you have proved the link of your equilibrium point problem with fixed point problem. And then you have shown a link of your equilibrium point problem with complementarity problem. Look at this. This is the 4th problem, a very well-known saddle point problem. This saddle point problem is defined like this. A and B be to any non-empty set. F is a mapping from A cross B to R. This point in A cross B is called the saddle point if this is satisfied. Look at this. What does this mean? F of x naught y naught is less than or equal to f of x naught y. So some sort of, you can feel a sort of increasing things over here. Then f of x y naught, this is less than or equal to f of x naught y naught. So you can see that x naught is fixed, but here, f of x is less than or equal to f of x naught. So loosely speaking, the above definition means that we have some feasible directions at the saddle point in which the function might decrease as well as the function might increase. So this is the concept of the saddle point. How this saddle point problem is linked with your equilibrium point problem. define this mapping. If you define this mapping by this, phi of A, B, C, D is equal to f of A, D minus f of C, B, f of C, B, and f of A, D minus f of C, B. If you define your mapping phi like this, what will happen? You find, I'm not going into the detail of the proof, this is very simple. What I want to tell you is when you solve your equilibrium point problem for this mapping phi, it will solve your saddle point problem for the mapping F. And when you solve your saddle point problem for the mapping F, it will solve the equilibrium point problem for the particular mapping phi. Then the existence of a saddle point problem is really very important in the non-cooperative game theory. Similarly, the Nash equilibrium point problem in non-cooperative game, this is something which is really important, that this Nash equilibrium problem in a non-cooperative game is equivalent to solving an equilibrium point problem of a certain mapping. So look at the beauty. If you want to solve the Nash equilibrium point problem in certain non-cooperative games, you need to solve an equilibrium point problem of a certain mapping. Let me briefly explain you what is the Nash equilibria problem in a non-cooperative games. Look at, suppose you have a family of non-empty sets, x1, x2, x3, xn. What is its significance? You can take x1 as a set of the strategies of player 1. There are n players in a certain game. There are n players. x1 is the set of the strategy of player 1. x2 is the set of the strategy of the player 2. Then x3 is the strategy of the player 3. And xn is the set of the strategies of the player n. Okay. Then you have these functions, hi from x to r. You can call these functions to be the payoff functions. I mean, when one player, say player 1, play with certain strategies given in this text, whatever he or she gets or lose is given by this function. So that is why we call it a payoff function. What is Nash equilibrium point problem? Nash equilibrium point problem is find this point, find a point in this such that the value of hi at this point must be greater than or equal to the value of hi at this for all xi belonging to xi. Please read this very carefully. If you look at this side, so this is your ith component. Your ith component is given by xi top 0. But if you look at this side, your right hand side, if I look at my right hand side, you will see that this point is not over here. This has been replaced by an element or strategy given in xi. And the payoff function at this point, if payoff function at this point is greater than or equal to the payoff function at this point for all the strategies, then this point is called a Nash equilibrium point. And if it is so, the last thing in solving Nash equilibrium point problem in non-cooperative game is again equivalent to solving an equilibrium point problem of a certain mapping. I have just given the following mapping. If you define this mapping F, if you define you mapping this phi from x cross x to r by this way, if you define a mapping like this, then if you find the equilibrium point of this mapping, this means you have solved Nash equilibrium point problem. And if you solve the Nash equilibrium point problem, this means you have solved this equilibrium point problem for this mapping F. So this is how your Nash equilibrium point problem is linked with equilibrium point problem. May I ask Hari Krishna how much time I'm left with?
Yeah, 5 minutes, Professor.
Okay, thank you. Thank you, Professor Prakash.
You complete 5 minutes, within the 5 minutes.
Thank you, thank you, thank you. Thank you for your patience.
Okay.
Okay. You can see slide now. Professor Prakash, you can see.
Yeah, I can
It
see.
is visible.
Yes, sir. Yes,
Okay.
sir.
So let me conclude now. The last problem is again very important problem that is named as the variational inequality problem. What is variational inequality problem? It simply says you take a closed convex set, say in H. For the sake of simplicity, I say H is a Hilbert space. Then you take T as a mapping from, say, K to H. The variational inequality point problem is the problem of finding a point X star in K such that whenever you take the inner product of Tx star with y minus x star, this inner product is greater than or equal to 0 for all y in K. So this problem is named as the variational inequality problem. This problem is a variational inequality problem. I just repeat it. You take the product of two vectors Tx star with y minus x star, and this product, this inner product is greater than or equal to 0 for all y in K, and this is a very well-known problem which is named as the variational inequality point problem. Okay, having said this, geometrically you can see this problem like this. A point X star is the solution of variational inequality point problem. If you take this vector Tx star, it forms an angle between 0 and pi over 2 with all vectors y minus x star for each y in K. So you find a point X star in K, apply T at X star, you get this vector Tx star. Tx star, take the angle of Tx star with y minus x star for each y in K. If this angle is between 0 and pi over 2, so this x star will be the solution of variational inequality point problem. Very quickly, this theory of variational inequality point problem was introduced in the 17th of the 20th century. Very effective method to solve a group of nonlinear boundary value problem for partial differential equation of elliptic or parabolic type. The pioneer work in that direction was done by Fichera and Stampecchia. Then the interest of the variational inequality problems declined due to the untimely death of Professor Stampecchia in 1978. Then Smith and Devermores formulated, look at this is the application. The variational inequality point problem is very much known because of its formulation of a traffic network equilibrium problem in the term of a finite dimensional variational inequality. So this problem was used to model this traffic network equilibrium point problem. And finally, I conclude my lecture with this slide. If I define a mapping phi from K cross K to R like this, again, please, this is the typo, this is not greater than or equal to 0. I define a mapping like this. If I define a mapping like this, then X star is the solution of equilibrium point problem if and only if X star is the solution of this variational inequality problem for this mapping. So what, so I conclude my lecture with this point. I started with the definition of a generalized mixed vector equilibrium point problem, and then we have shown that this generalized mixed vector equilibrium point problem unifies a lot of research problems. Then we have finally checked that this equilibrium point problem is very much again linked with a convex optimization problem, complementarity point problem. It is linked with the fixed point problem of a multi-valued mapping. It is linked with variational inequality point problem, and then it is linked with Nash equilibrium point problem. So thank you everyone. Thank you for your patience.
Dear participants, any questions?
Hi, good afternoon,
Yes.
everyone. Thank you very much, Professor Abbas. Very nice talk. I didn't know about this generalized equilibrium problem. I think it's very interesting, so thank you very much. Congratulations. My best regards and wishes.
Okay, I conclude this session. So thank you, Professor, for giving your nice talks. And so thank you, sir. Thank you.
Thank you.
Everyone.
Thank you, everyone.
Thank you.
Thank you. Thank you. Thank you. I will be very happy. I really appreciate the way you have organized this conference. I congratulate you. Thank you.
Thank you.
Thank you.
Thank you, Hari.